Sometime in the last few years, engineers inside a Chinese semiconductor facility did something extraordinary and catastrophic. They had gotten their hands on one of ASML's deep ultraviolet lithography machines, a $550 million piece of equipment, arguably the most precisely engineered industrial tool on the planet, and they took it apart, not to use it, to understand it, to copy it, except they couldn't put it back together. So they did the only thing they could. They called the ASML and asked for help fixing the machine they just tried to steal the secrets from. When ASML technicians arrived, they immediately knew what had happened. You don't just break a lithography machine. You break one by disassembling it without understanding what you're doing. That single moment tells you everything about where this race stands and where it's heading. Why one Dutch machine controls the world. There is a company in the Netherlands that almost nobody outside the tech industry has heard of. It employs 42,000 people. It has a market cap larger than most banks. And without it, your phone doesn't exist. Your laptop doesn't exist. The guy you're talking to right now doesn't exist. ASML makes the machines that make the machines that make the chips. Specifically, they make lithography tools devices that use beams of light to etch circuits onto silicon wafers. Circuits so small that the lines are thinner than a strand of DNA. Circuits that only exist because ASML spent 30 years and billions of euros figuring out how to generate a specific kind of light that nobody else on Earth has reliably manufactured at scale. That light is extreme ultraviolet, EUV, just 13.5 nanometers in wavelength. To produce it, ASML's machine fires a CO2 laser at droplets of molten tin 50,000 times per second inside a perfect vacuum. The resulting plasma hits temperatures of 200,000 degrees, Kelvin 40 times hotter than the surface of the sun. That plasma emits EUV photons. Those photons bounce through a series of mirrors polished to within the width of an atom. And eventually, they land on silicon printing circuits that define the most advanced chips in the world. ASML is the only company on Earth that can do this commercially. One company, one machine, one choke point for the entire global technology stack. And China doesn't have it. That is the problem Beijing has been trying to solve by any means necessary. The embargo and the panic in 2019, under heavy US pressure, the Dutch government quietly blocked ASML from shipping its most advanced EUV machines to China. No explanation needed. The message was clear. China would be locked out of the leading edge of chip manufacturing possibly indefinitely. For Beijing, this was an existential alarm. Chips aren't just consumer electronics. They're the foundation of military systems, of economic sovereignty. A country that can't make its own advanced chips is, in the long run, a country that runs on someone else's infrastructure. So China did three things simultaneously. First, it stockpiled. Chinese chipmakers like SMIC rushed to buy every older ASML DUV machine they could before additional restrictions tightened. By some estimates, 42% of ASML's quarterly revenue in late 2025 still came from China buying older, less restricted tools in bulk. Second, it tried to build. State-backed companies like SMEE Shanghai Microelectronics Equipment received massive government contracts. By 2025, SMEE had gotten its 90-nanometer lithography system into mass production and was entering the verification stage on a 28-nanometer immersion tool. Significant progress, but still a decade behind ASML's commercial capability. And third, it started taking things apart. The break-in, the story of the broken DUV machine became public because of the absurdity of what happened next. The engineers called the ASML's service team, and ASML bound by service contracts sent technicians. What the ASML engineers found wasn't a malfunction. It was a machine that had been meticulously disassembled and improperly reassembled, alignments destroyed, precision optics disturbed, years of calibration gone. Here's what most coverage of this story misses. This isn't evidence of failure. It's evidence of desperation and of just how insanely complex these machines are. A modern DUV immersion scanner has dual wafer stages moving at high speed simultaneously. Its optics maintain overlay alignment to within 2.5 nanometers, roughly 25 atoms. Its throughput reaches 3,300 wafers per hour. The entire system is a ballet of physics, so precisely tuned that even licensed operators with factory training can't simply open it up. You can't reverse engineer this machine the way you reverse engineer a car engine, or a phone, or software. And China found that out the hard way. The secret lab in Shenzhen, but here's where this story gets genuinely alarming for the West. In December 2025, Reuters broke a story that sent shockwaves through the semiconductor industry. Inside a classified compound in Shenzhen, workers given fake names, classified under national security, the entire project invisible to the outside world. Chinese scientists had done something nobody thought possible this soon. They had built an EUV machine. Not a production-ready one. Not one that can make chips yet, but a prototype that generates 13.5 nanometer EUV light using the same laser-produced plasma method that ASML uses. Completed in early 2025, occupying nearly an entire factory floor. Built by a team that included former ASML engineers who had, according to Reuters sources, reverse-engineered ASML's own technology, would need many, many years. The previous CEO had said China was light years behind. Neither of them was expecting this. The project is enormous in scale. Huawei is reportedly coordinating a web of state research institutes and private companies, thousands of engineers working on different components, a level of national mobilization that one source compared to the Manhattan Project. Beijing's official target, working chips from this machine by 2028. The realistic estimate from people inside the project, 2030, still years away, but years not decades. Why this is harder than it looks? Before you conclude that China has cracked it, let's be precise about what they actually have. They have a machine that generates EUV light. That is genuinely remarkable. But generating EUV light is one piece of maybe 200 critical pieces. And several of those remaining pieces are arguably harder than the light source. ASML's EUV machines rely on mirrors made by Carl Zeiss in Germany, mirrors polished to atomic-level smoothness, with surface errors measured in fractions of a nanometer. These are among the most precisely manufactured objects in human history. China cannot currently source them. Carl Zeiss is blocked from selling to China. China's domestic optics industry is nowhere near this capability. Then there's the software. ASML's machines are tuned in the field, constantly updated, with decades of process knowledge baked into control algorithms that nobody outside of ASML fully understands. The machine learns the wafer. It compensates for vibration, temperature drift, stage error in real time. And there's the supply chain. ASML integrates components from nearly 5,000 suppliers across dozens of countries. Laser systems from Cymer in California. Vibration isolation systems from specialized European firms. Metrology tools calibrated to standards China doesn't yet have. As Morningstar analyst Javier Correonero put it, even if China can produce some EUV light, turning this into an economically viable manufacturing process could take years, if not decades. China has a light source. It doesn't yet have a lithography machine. The lane change, China's photonics gamble, but here's the angle that almost nobody is talking about. While the world watches China try to copy ASML, China might be preparing to make ASML irrelevant. Remember, the entire reason EUV matters is because silicon chips need smaller and smaller features to get faster and more powerful. EUV is the tool that makes features smaller. But what if the future of computing doesn't run on silicon transistors at all? China has been investing heavily in photonic chips processors that use light instead of electrons to move and process information. Photons travel faster, generate less heat, and consume dramatically less energy. And crucially, photonic chips don't require EUV lithography. They're built at larger node sizes, using equipment China already has. In June 2025, Shanghai Jiao Tong University's CHIPX facility completed the world's first production line for thin-film lithium niobate photonic chips with annual capacity already surpassing similar lines in Europe. In November 2025, CHIPX unveiled a photonic quantum chip with more than 1,000 optical components on a single wafer, claiming performance gains over conventional processors for specific AI tasks. Separately, researchers announced the Meteor 1 optical parallel computing chip, achieving theoretical performance on par with high-end GPUs using light. And China's LightGen optical AI chip, developed at Shanghai Jiao Tong and Tsinghua University together, is targeting the exact workloads that NVIDIA dominates: matrix multiplication, neural network inference. China is investing in post-silicon computing more heavily than any country on Earth. Its research institutions are reportedly producing more than double the US research output on post-Moore's law technologies. The strategic logic is clean: if you can't win the current game, change the game. Section 7. Let's take stock of where we actually are. China broke a DUV machine trying to understand it. That's embarrassing, but it's also a data point. It tells you how seriously they're taking this, and how steep the learning curve is. China has built an EUV light source. That's genuinely ahead of where Western intelligence thought they'd be. It is not yet a lithography machine, but the trajectory is real. China has its own domestic DUV tools, SME at 90 nanometers in production, 28 nanometers in development. Not competitive with SML, but progressing steadily, year on year, with state backing that doesn't require quarterly earnings calls. And China is pursuing alternative architectures, photonics, neuromorphic computing, chiplets that don't require Western lithography at all, architectures where the playing field is less tilted. The semiconductor sanctions were designed to freeze China in time. What they actually did was create the most motivated, best-funded semiconductor RAN program in human history. China's semiconductor equipment sector has set a target of 70% domestic sourcing by 2027. They're not waiting for permission. ASML's monopoly on EUV is real, and it's durable for now. But monopolies built on complexity are only as durable as the complexity advantage holds. China proved it could build world-class cars when everyone said it couldn't. It proved it could build world-class AI DeepSeek trained on older, restricted chips by writing low-level GPU code that Western engineers hadn't bothered to optimize. It proved it could build jet fighters capable of downing European-made aircraft. The question isn't whether China will close this gap. The question is how and whether the world has a plan for when it does. The man who broke the ASML machine thought he was taking a shortcut. He wasn't. He was learning at great expense exactly why these machines take decades to build. But learning is the first step. The real question is, what happens at step 2, and 3, and 10? Because the history of technology is not a history of monopolies that held forever. It's a history of walls that everyone said couldn't be climbed until someone climbed them. And right now, in a classified compound in Shenzhen, somebody is staring at a machine that generates EUV light, thinking about what comes next.